This video covers content in your lecture notes from Chapter 1, Section 8. We'll start with a definition. We need to define what a variable expression is. We will use the term expression quite a bit, but a variable expression is a combination of one or more variables with numbers. We may also have some arithmetic operations like addition, subtraction, multiplication, division, exponents, you name it. Some examples of these might look like 3a plus 5. Notice that there's a variable a in there. There's also numbers 3 and 5 in there, and the arithmetic operation of addition. Another example might be x squared plus 3x minus 10. Again, we've got a variable of x in there. We've got numbers in there, and we've got arithmetic operations. For a third example, we might write something like y plus 5 divided by y minus 3. Now we have the variable y, we have some numbers, addition, subtraction, and division. So those are variable expressions. Notice that what these don't have is an equal sign. That would make them equations. For example 1, we're going to turn these words into variable expressions. For part A, we're given the phrase 9 more than a number. When you see something like a number and you don't know what that number is, it's a variable. So pick a letter to represent your variable. Maybe for this one, I'll use the letter A. Now I want 9 more than a number, or 9 more than my variable A. So I could write this as A plus 9. You could also write this as 9 plus A. Same thing. You can also use any other letter for your variable. You don't have to use A. Let's look at D. This time I have a number divided by 6. Again, here's that number that I don't know what it is. It's a variable. So maybe this time I'll use an x. And I need that number x divided by 6. So I might write it as x over 6 or x divided by 6. I could also write this as x divided by 6, but we won't use that notation very much in this class. Let's go on to example 2, where we will start evaluating algebraic expressions. When we evaluate an algebraic expression, that means that we want to substitute a value or a number for a variable, and then we're going to simplify what we have. Let's look at A. We have 5x plus 2, and what we need to substitute is 11 for the x. So we're going to suppose that the variable x equals 11, substitute that in, and simplify. So if I put 11 where the x is, I have 5 times 11 plus 2 instead of 5 times x plus 2. Now using good order of operations, I'll multiply first. Doing 5 times 11 is 55, then add the 2 to get 57. Let's look at part C. In part C, I now have x squared minus 13x minus 40. That's my algebraic expression. And I need to substitute, evaluate with x equal to negative 8. So everywhere in the expression where you see an x, we need to swap that out and put a negative 8. So instead of x squared, we have negative 8 squared. Parentheses are important here. And instead of negative 13 times x, we have negative 13 times negative 8. And finally, our minus 40. Using good order of operations, we will do our exponents first. Negative 8 squared, that's negative 8 times negative 8, or positive 64. Again, using good order of operations, we'll move on to multiplication. Now we have negative 13 times negative 8, which is positive 104. Finally, we can move on to addition and subtraction in order. And if we have positive 64 plus positive 104, that's positive 168. And if we subtract off that 40, we get 128. Let's look at E. In part E, we have b squared minus 4ac. Notice in this one that we have 3 variables, a, b, and c, and we're going to substitute for all of them. Let's do them one at a time. Instead of b squared, we're going to use 5. So we'll have 5 squared. Instead of A, we'll use -1. And instead of C, we have 18. Let's simplify using good order of operations. We don't have anything that needs to be simplified inside our parentheses, so we can look at our exponent. We have 5 squared, or 25. Now we can move on to multiplication and division. So we need to multiply -4 times -1, then times 18. So we have 25 minus -4 times -1, that's +4. So that becomes a +4 times 18. 4 times 18 is 72. Now we can move on to addition and subtraction. 25 plus 72 is 97. And we've now evaluated that expression using A is -1, B is 5, and C is 18. Next, we're going to talk about the distributive property. If you have any real numbers, A, B, and C, and you have A times the sum of B and C, this is the same thing as if first you did A times B, or AB, and then A times C, or plus AC. That's the distributive property. And I will always draw it with those arrows to show how I'm distributing A times B and times C. Let's look at example 3 and practice using this distributive property. We have 7 times 5x minus 4. Using the distributive property, I can first do 7 times 5x, which is 35x. Then I can do 7 times -4, which is -28. Let's look at C. In C, we have 12 times, now 3 terms inside of parentheses. And the distributive property works just the same. I can distribute the 12 to each term inside the parentheses. So when I do 12 times x, that's 12x. Then I can do 12 times -2y, or -24y. Then 12 times +3z, which is +36z. Let's go on to part E. In part E, we have -6 times 4x plus 11. And I'm going to distribute that -6 to each term inside the parentheses. First, we have -6 times 4x. You can also think of that as -6 times 4 times x, or -24x. Next, we'll distribute the -6 to the +11. -6 times +11 is -66. And again, we've used the distributive property to simplify this expression. Let's talk a little more about these expressions and parts of an expression. Here's an example of a variable expression. Variable expressions have a few different parts. One is that they have terms. Each of these parts of the expression, separated by addition and multiplication, are the terms of an expression. In other words, these terms are x cubed, -x squared, +23x, and -59. In other words, this expression has 4 terms. Let's talk about the constant term. The constant term is the term that does not have any variables. So in this case, our constant term is -59. Last, let's talk about our coefficients. Coefficients, those are the numerical factors of terms. So the coefficient of a term is the numerical factor of that term. So on our first term here, x cubed, there's nothing written here, but you could think of it as 1 times x cubed. So the coefficient of that term is 1. The second term is -x squared. Again, it might not seem like anything's written there, but you can think of that as -1 times x squared. So that coefficient is -1. On our third term, The positive 23 is the coefficient, and of the constant term, it is its own coefficient, negative 59. That is, our coefficients are 1, negative 1, 23, and negative 59. Let's look at example 4. In example 4, we need to determine the number of terms, list them out, and then state the coefficient of each term. A quick check shows us that we have 1, 2, 3 terms. Now let's list out those terms, and we'll also then give the coefficients that go with them. Our first term is that first chunk, 8x cubed. The coefficient of that term is the numerical piece, which is 8. The next term is negative x. Again, it may not look like there's a numerical value there, but it's really the negative 1. And then our last term is our constant term, negative 17, and the numerical factor of that is negative 17. So we have 3 terms. The coefficients are 8, negative 1, and negative 17. Let's go on to talk about how we combine like terms. Like terms are terms that have the same variable factor with the same exponents. If the variables and exponents match, they are like terms. On A, look at 3x and negative 5x. The variable here is x, and the exponent of that x, it's not written, but it's really just a 1. 3x and negative 5x are like terms because they have the same variable with the same exponent. That is, we can combine them. Let's write them next to each other. Now, look at 7y and plus y. Those two terms have the same variable of y, and they're also just to the first power, so they are like terms. Let's also write those next to each other. At this point, I have not changed the expression at all. I've just simply reordered the terms. Sometimes it's helpful to think of our variables as objects instead of just letters. So let's think of x as dollars. So if I have $3 and I owe you or take away $5, how many dollars do I have? I'm in the hole $2. For y, let's do the same thing. Let's talk about y as apples. If I have 7 apples and I get 1 more apple, I now have 8 apples. So I've now combined my like terms. We could also write this as 8y minus 2x. Just looks a little cleaner. Let's go on to C. Let's go on to example 6. In example 6, we're going to combine what we've learned so far in this lesson. Notice first that I have 5 times parentheses 2x plus 3. We can use what we learned about the distributive property to simplify this first chunk. I can do 5 times 2x and 5 times 3. 5 times 2x is 10x, and 5 times 3 is 15. The rest we'll just copy down. Now let's talk about combining like terms. The first pair of like terms that I see is the 10x and the 9x. They both have a variable x to the exponent of 1. I have 10x and 9x combined for a total of 19x. Now let's look at positive 15 and negative 8. They are like terms in that they're both constant terms, and we can combine those as positive 15 take away 8 or positive 7. So we've now simplified this expression by using the distributive property and combining like terms. Let's go on to part C. Part C has 2 sets of parentheses, so we'll be able to use the distributive property twice. With our first set of parentheses, we can distribute 3 to the 2x, or 3 times 2x, 6x. Then we can distribute the 3 to the negative 7 to get negative 21. With our second set of parentheses, we can do the same thing. I have negative 8 times x, or negative 8x. I also then can do negative 8 times negative 9 for a positive 72. It's really important to note that this negative in front of the x needs to get distributed with the 8. It stays with the 8. Now let's combine like terms. First, I notice that I have a positive 6x and a negative 8x. Let's have the same variable with the same exponent. That's a total of negative 2x. Next, I'll look at the constant terms of negative 21 and positive 72. Combining those two together, we get a positive 51. So now we've simplified this expression using the distributive property twice and then combining like terms. And that's the end of this lesson.